All right, good morning, everyone. So welcome to the 10th lecture. Time is passing very fast. Today we'll be talking about sequence alignment, which is a very important topic. This step used in really too many ways, but we will see a very important way where we use it in read mapping, and you are going to implement that. So please pay attention to that. Last time we went through 4 main steps in read mapper, and we already spent too much time in indexing step. Last time we covered seeding, and it's really not different from indexing, except the part that we don't store in the hash table those seeds that we extract out of the seeding algorithm. However, the algorithm is exactly the same thing. And you can see in the table of content that you have a programming assignment related to this and this, right? We'll go over the details by the end of the lecture. For pre-alignment filtering, it's really not important except the part that it's trying to improve the performance. So it's up to you. If you don't want to include the pre-alignment filtering and you want to send all the pairs that you detect out of the hash table based on the similarity on the seeds, you could send directly those pairs to this step, right? However, this will be very expensive computation. So your read mapper will really suffer if you do that. For that reason, we are going to jump from here to there. We will skip this part for now, but we will cover it later on. After 4 lectures or so, we're going to jump into the pre-alignment filtering. Why is that? I really want you to see the suffer, to see the cost that we are going to pay once we use directly sequence alignment without pre-alignment filtering. And that will motivate you for the need for that step. This step is really an additional step that's going to filter most of those candidates based on the figure that we saw together in here. If you still remember this slide, this very important slide, and you are going to face the exact same issues that we will face over here. So this is a read sequence. Let me maybe move the video a little bit. Okay, this is a read sequence, right? And this is a reference genome. We try to extract those seeds. Think about, anyway, regardless, we already studied around 10 algorithms to extract those seeds. But regardless the way, imagine that we have this seed, and that seed. And we could have anything in between over here, okay? Those X mean don't care, okay? Now, imagine for each of those corresponding seed, we got a bunch of matches over here. So this blue seed matches over here, 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 here. Likewise with the red and the green, as we can see from here, right? And if still remember, we said that this is the good guy. This is what we are looking for. And all the rest are just noise, just things that we really don't want, right? And only this guy deserves to be further investigated, right? Because we have very high similarity in regards of the seeds and in regards of the order of those seed matches. So not only the seed itself, the seed content is important. However, the order of those seeds is really important as well. For example, in here, we have the red, blue, and green. So all of them matches. However, the order is tweaked. So that's why we don't think that this area is really going to be similar to the read sequence. So that's why we ignore it. So it's important to get the matches as well as the order of that seeds that we extract from the read. Now, only this guy going to be sent for sequence alignment. Sequence alignment is a step going to give us 3 important things, and we are going to see them very soon in the next slides. All right, and we saw this example. If I ask you to find this AACC in this text, you're going to give me all those locations, right? This is a very nice example, very smooth, straightforward. However, in real life, we don't have smooth thing. So imagine if I'm trying to match this to this. Can I consider it as perfect match? How about this? How about that? How about this? Right? So that is going to open a question for me. how many differences I can tolerate in order to say that this guy is similar to this. So if I have a threshold and I define it as 2 differences, then those guys could be recognized as similar to this, right? If I have 2 differences, the same story. But once I start exceeding that threshold, then I no longer can recognize those differences. It's not the time for this. And this directly opened the question how to examine the similarity between the read sequence and each sequence in the reference genome. We already detect this region, but now we don't know how similar, how different are they, right? There's a very practical example, and I'm sure all of you face this example. You misspell some of the word in Google search, and then directly Google give you some suggestions. How's that happening? How does Google know that you meant to write this word instead of the misspelled word, right? And normally it's done using any of those methods, which is text similarity detection. And we are going to see the very first trivial way to doing that, which is called Hamming distance, right? Okay, Hamming distance is not something new. It's very old, very fundamental paper. The author of that paper called Richard Hamming, which is mathematician. He's very famous American scientist. And this paper was published in 1950. It was not meant to be used in genomics. It was meant to be used in computer networks, okay? We send from one place to another place a bunch of data packets, and we would like to have a way to verify the correctness of those packets. Because sometimes a distortion could happen to the signal sent from one place to another, especially if it is wireless. And now we need a mechanism to recognize that there is something wrong happened to one of the packets along the way from the communication medium, okay? And that was the Hamming distance method. So how it works? So the minimum number of substitutions, and this is very important, substitutions only, required to change the read into the reference segment. So if I give you one example of text and another text, and this is the correct version, and this is the distorted version. And I ask you how many errors happening along the way when I transfer one of the data to another. So Hamming distance is saying you need to count how many substitutions error happening. Substitution mean just replacing one character by another, okay? So it does not recognize insertions, does not recognize deletions. So just recognize if this letter is A and get replaced by C, then I'm going to count this as single change, okay? And then I say Hamming distance of 1, meaning the difference between this and this is 1 substitution, right? So here's an example. This is perfect match, the exact same text. I'm trying to compare this with that. And what is the Hamming distance of this? Perfect match, no change. What is the Hamming distance? 0, excellent. Yeah, this has a Hamming distance of 0. And then we represent it using H uppercase, parentheses. And then we have the first text, comma, second text equal 0. This is how we write it, okay? Now, if I make 2 changes, what is the Hamming distance? 2, excellent. So now it's 2 because I made 2 substitution changes. 1 and 1, 1 and 1, okay? And the rest are perfect match, yes? Excellent question. So normally, this is a very nice example where we show it in terms of text. How about a collection of text? So you could use the exact same term for a collection of set of data with another set of data. and then they represent it as a distance. There are many other alternatives to the distance, for example, Euclidean distance, and too many other things. There are a bunch, around 6 distances could be used. There is also Earth moving distance, another term. So it's very famous to use the term distance in those kind of data. But think about this as 2D data. And this is where the very famous examples for those metrics to be used. For example, the XY coordinates could be geolocation, could be anything. And then you represent some data, right? And you'd like to measure or cluster them, which is machine learning, for example. So one very famous way to use clustering over here is K mean distance, right? Or K mean clustering. So you take the mean out of this group, the mean out of that group, and then cluster based on that. Then you said we have 2 important clusters. However, if you have something nearby over here, then it will be tricky. Should I define this point as part of this cluster or that cluster? Okay. So the term distance is very famous. It's well known in data science. Okay. But that's very, very good question. It's really good for researchers to always question the things. Why we do it this way? Can we do something better than that? And so on. This will open up the research questions, and then you may come up with a new way of doing that. All right. So the Hamming distance is computed in linear time. Why is that? Very cheap, computationally really cheap to do that. You just need a for loop. You iterate over this first character. Is it similar? Yes, then 0. If it's not similar, increment the distance by 1. As simple as that. Very easy to do. That's why we call it linear time. Okay? So there are 3 main properties that they are very important. The first one, the Hamming distance between the sequence and itself, 0, right? Very trivial. The Hamming distance of sequence and another sequence is exactly the same thing as the Hamming distance between the second sequence and the first sequence, right? Makes sense. Because it doesn't matter where's the location of those differences. As long as it's substitution, then I'm going to count it as 1, right? Now, the third one is a bit tricky. So the Hamming distance between the first sequence and the second sequence, plus the Hamming distance between the second, which is here, and the third one, meaning that if I have one sequence and another, and then this one, maybe you could have it as a black, and then the third one over here is 1, 2, 2, and 3. So the Hamming distance over here plus the Hamming distance over there is greater than or equal the Hamming distance between the first and the third. The first and the third. Now, when you see such equation, it's always very good practice for simplicity to consider the equal sign. So ignore the greater than sign, consider it as equal sign, and think about it. If you see something logical, then you continue with the greater than sign. For example, this and this, when it could be equal? When the Hamming distance over here plus here could be equal to this. Excellent, right? How about all of them are the same? Then Hamming distance here, 0, 0 equals 0, right? That's a very straightforward example. That's excellent. Now you can start thinking about other ways where this could be greater than. What if we have single difference between this and this? Okay. And then this could be very similar to this, or also having a single difference. Then this one and this one could be considered as a reference. if this is different from this, and this is different from that, then probably this and this are different. And if single change based on this and this, because this is used exactly as is, as a reference to compare this and that. And this is used to compare with this and that, but maybe the change is here, but the change here is in a different place. But still, they differ by one place. And then when I compare this and that, then it will be also one place or two places. So here in the beginning, and here it's very similar, so it means this will be different from that in the beginning, right? And here is different from that, but here this is very similar to this. Then this is going to be different from that as well by the second location. It means we will have a difference here, and we will have a difference over here. In this example, 1 plus 1 equal 2, right? And you can think about too many other ways of how this still holds. Okay. Any question? Yes. Excellent. So that's, yeah, very nice question, because practically you're going to face that. If you choose Hamming distance in the programming assignment, you will face some cases where the read is always fixed, right? Because this is given. You cannot control it. But what you can control, the other side, which is the subsequence we're going to extract from the reference genome. Remember the previous example? Let's go quickly. In here. So I know those three places are exact match, right? But when I'm going to compare the read with the region over here, how far should I pick the other characters? Last time we discussed, normally we go with a little bit of margin over here and a little bit of margin over there. But how far? Is it 10 character, 5, 20? We discussed last time, there is a tool called Minimap2, which is one of the famous read mapping. Try to not pick any margin over here. Whenever we got exact match in the beginning, we consider this is the beginning of the subsequence coming from the reference genome. So we start picking from here all the way with the distance equal to this plus some margin, okay? So back to your question, how I could apply the Hamming distance for a read. It's a fixed length, let's say 100, right? Say this is 100. And a reference subsequence that we just pick from here, which is, let's say, 110. We just pick a little bit of margin over here. Now, Hamming distance definition won't change. It's still exact same thing, which says, go for a loop, first character to first, second to second, third to third, keep comparing. Over here, you won't see anything, right? So you can consider this as a mismatches. Okay, so you can continue counting this, and that will give the Hamming distance as a plus 10. So we know already in advance that those are differences, right? And I'm having another example which trying to show the question that you asked. But before that, the implementation, we already discussed it, right? Let's go over it. So if you'd like to implement it in Python, you just define a function, a distance initialized by 0, and you measure the length of one of the strings. Normally, you should go with the maximum out of those two, and you consider it as the length. And then you go on for loop. However, if you consider the maximum over here, you might get out of boundaries error over here. So you could consider the minimum, and then you add this number up again, or you consider the maximum, and when you arrive here to the length, you just skip, you don't compare, but you still add the 10 errors to the margin. It's up to you how you implement it. However, the implementation or the important part over here is the for loop. And here we just compare the character by character. If it is not similar, just add 1 to the distance. As simple as that. Any question? You can try it on your own and hear how you test it. Now this is the example. All right, I'm going to have this text and this text. What is the difference between the two? Just one character added, insertion. It's not substitution, okay? Just add one character, this and this. So this makes this text longer than the other text by one character, right? Now, when I try to compare, try to calculate Hamming distance, I got only 2 matches. Only 2. Why? Try to do it yourself. Compare the C with G, C with G, A with G, A with C, G with C, C with G, A with C, and A with nothing. None of them match each other, right? And then the Hamming distance fails in calculating the right distance between the 2 words. The distance is only 1, but Hamming distance giving you 7. There are 7 mismatches. So a single change causes a Hamming distance of 7 steps. Now that opens another question, where we can use Hamming distance and where we shouldn't use it, right? So if you shouldn't use Hamming distance, there is a very nice alternative to it called edit distance, okay? Now again, why we call it distance? The exact same philosophy, right? Okay, so edit distance, let's see what is it. Now the minimum number, which is very similar to the Hamming distance definition, right? Both of them considering the minimum number. However, this is the important difference. The minimum number of edits. The minimum number of edits. And what do we define the edit? Last time we defined it as insertion, deletions, or substitutions. And we call the insertion deletions as indel. You will see this term in very large number of papers. Indel mean insertions or deletions, okay? Or both of them. So it's the minimum number of edits needed to make the read exactly match the reference segment. And we took several examples last time, like, you remember the example? Consider? Like Switzerland and Netherlands, when we try to compare them and we see different ways of how we could arrange those characters, that is edit distance. So now we consider the exact same example in the previous slide. You still remember it? We have the exact same text and we make one insertion over here. In edit distance, if you want to solve that, we would fix it this way. We really, when we have insertion, we make a gap in the other sequence and then we try to compare it. And now when we try to compare it, we get the right number of differences between the 2 texts, okay? Now, this is the thing we discussed last time. So if we try to compare organization and translation, you'll see something like that. However, you may have different ways of doing it. So here, we consider the gap to be here, but here we consider it to be in different way. But still the number of differences, which is edits, right? It could be substitution, insertion, or deletion, still 5. Here it's 4. And now which one we pick? We pick the minimum always. That is in the definition itself, okay? But how we calculate that? How we do the calculation itself? How we know it's 4 differences? How we know it's 5? Now let's take an example that's hopefully going to introduce you a little bit to the edit distance algorithm. Because it's a bit complex, we need to go gradually, okay? Now I have the word Atlanta and Atlanta. Or some people spell it as Atlanta, okay? So we have Atlanta and Atlanta, would like to compare them. They are exactly the same thing, okay? How many differences? None. All matches. And we know that in advance. Edit distance 0. Now I would like to delete one thing, which is A. Excellent. So I'm going to delete the A in the middle, right? And now I will compare this to that. Now when I delete something over here, when I delete this one, what happened to all the trailing character? We call those as trailing character. The things coming after the change. What happened to all of them? So remember, there is one character deleted from here. So all the trailing character get shifted to the right, right? So the deletion caused all the trailing character to be shifted by one place. If we have two deletions, it will be shifted by two places. And when we compare, you will see the comparison is also shifted. When we compare this character with that, now the comparison itself is shifted by one place. So instead of comparing the corresponding characters as in Hamming distance, now we are comparing the original character with the shifted version of the previous character. Okay? And we do that for all the trailing. And this is how the edit distance is going to calculate the distance correctly. Now let's see the opposite effect. By going to insert character, not delete character. But remember, we return back the A, the one we deleted, because we go back to the original version. Okay? And we inserted one character, which is green, right? Now, when we put something in the middle, what happened to all the trailing characters? Shifted in the opposite direction, to the left, right? And what will happen to the comparison? Comparison is also shifted to the right, right? But how do I know in advance, should I compare this with here or with here? So if it is a deletion, I should compare it to here, right? If it is an insertion, I should compare it to here. If it is exact match, I should compare this and this. So since I don't know in advance, right, I could be given totally random sequences for the comparison. And I don't know, where should I compare? Should I compare this character to here or there? And now if there are two insertions, things becoming more complex. Instead of comparing this with this, I'll be comparing this with that, right? Think about two boxes of this are inserted. So as long as I keep inserting, I would like to keep shifting this and compare this with this, or this with that, or this with here. What is the limit? When I should stop? So, trivial way, I should stop by the end of the sequence. There is no more character to be compared, right? So I cannot compare anything over here with here. That's the first way to stop. The second way to stop is to have a limit on the number of edits. If I know in advance that I'm allowed only to discover 3 insertions, then in theory, I should not move more than 3 steps. Then I should compare this with this. That's first step, second, and third, right? I should not go further and compare with the 4th step because I'm allowed only to tolerate 3 edits, okay? That's another way to look into it. And for that, to have the algorithm for this, I really need to consider all the shifted versions of the text. All the shifted version of the text. So this is the original text, and this is the text I'd like to compare with. So I pick one of them, which is this, the second, and I would like to shift it all the way until I finish the length of that text, okay? So I shift it by 1 step to the left, 1 step to the left, one further, and so on, until no more character could be shifted. So this will be compared with the first. If I shift more, then this will be compared with nothing over here, okay? Why I'm doing this? Remember, which one causes the shift to the left direction? Insertion or deletion? Insertion or deletion? So insertion, I'm going to push something, then everything will be shifted to the right. When I delete, everything will be shifted to the left, right? So this one is caused by deletions. This group caused by deletion. And the other group is caused by insertion, right? And since I'm doing all this all the way until the last character, then I'm considering all number of possible deletions, right? Likewise, over here, I'm considering all possible ways of inserting a character, right? I could insert one character, 2, 3, 4, and 5. Now, why I'm doing that? Why I'm doing all of those copies and all of that copies? Because simply, I don't know in advance how many inserted character, how many deleted character could be, right? So I could be giving any random sequences to be handled and calculate the distance for those sequences. So since I don't know, I need to consider all the ways to do that, all right? Now, there could be an exact match. That's why I keep the original. So keeping the original is very important. So I hope I have the copies over here, other copies, but I also keep the original. Now, what should I do? Every time I have a new copy of the text, regardless if it is shifted or not non-shifted, I always compare it with this and calculate the Hamming distance. The Hamming distance. Although I'm calculating the edit distance, but I really would like to calculate the Hamming distance for each pair of those sequences. This one, sequence 1, and any of those in the list, okay? So let's compare the sequence 1 with sequence 2 doing Hamming distance. Then I figure out that there are exact matches, and they are already colored in orange. So the orange color means they are exact match with sequence 1. So you can see there are 3 characters over here, another 3 characters matching with this. Now in here, I see all those bunch of sequences or bunch of characters are matching with the corresponding characters over here. Likewise in here, in here, in here, in here, and there, and there, okay? Now, what does all of this telling us? So this is telling us if you do no shift, you will get only 6 matches. Here, if you do single shift, you will get 1, 2, 3, 4, 5, 6, right? And now, if I have a greedy choice to choose which one providing the largest number of exact matches, then I would go for this one and this one. Why? Because those two are the 2 sequences that provide the largest number of exact matches. Here, I don't see much of orange characters. Over here, exactly the same thing, right? Although this might be the second largest, so this could be alternative way of looking at this sequence, but this providing me the largest number of matches. And remember, the definition of edit distance was the minimum number of differences, right? And that is equal to the largest number of matches. That's why I'm looking always for the largest number of orange. And then, remember, this is shifted by one version of this. So this is telling me that the first portion of the sequence are exactly the same thing, and then something happened over here, exactly over here, that cause those characters to be matched by shifting them to the left direction. And we know already if the comparison happening to be in the diagonal toward the left side, then there is a deleted character. So this is telling us that there is a deleted character over here that caused the A over here to match to the left corresponding character over here. Likewise here, 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 and then, and so on. Okay? And now, since we consider all the deleted, all the shifted version to the left and the right, then we could detect any kind of differences, regardless if it is deleted, inserted, and so on. Now, coming back to a golden comment, he was mentioning, what if we shift to the left or shift to the right? Should we consider left or right, right? Now, if you do the opposite thing between sequence 1 and 2, if you consider 1 here and 2 over there, and then you try to shift sequence 1 instead of shifting sequence 2, then the one shifted to the left will be shifted to the right, and the one shifted to the right will be shifted to the left. So it really depends on where you're looking. Are you looking for sequence 1 or sequence 2? Over here, we consider all shifted version of sequence 2. What if we consider all shifted version of sequence 1 and we try to compare them with sequence 2? Try it yourself and you'll see totally the opposite effect. So instead of this matching with the shifted version over here, it will be matching with the shifted version over here. Okay? Because in here, imagine this one I'm comparing with that, not the opposite. In here, in this example, we are comparing this with that, and we said this character will be compared to the right. But if we are looking at this sequence, then this character will be compared to the left, not to the right. And this is exactly what will happen. So it depends on which one you consider as a reference and which one you consider as a read. Okay? So in your program, you're going to have the fast queue and the FASTA file, right? You're going normally to consider this as a reference and this as a read, okay? I'm going to pick one sequence from here, try to find the location in the very long sequence, and you might get a bunch of location over there. Now, for this, when you start reading the file, yeah, it's clear that this will be a reference because this is the longest, the largest genome, right? And this is very short sequences. But the moment you pick one sequence from here and a bunch of sequences after indexing and seeding, now the length is almost the same, right? So you might do this wrongly, that you consider this as a reference and this as a read because the length is the same. And this is going to change the way you are looking to the differences. So I might give you the two sequences, the exact same sequences, to two of you, okay, like Prague and Golden. I'm going to give you the pair of those sequences, exactly the same. But your software is telling me there is one insertion, and your software is telling me there is one deletion. Which one is correct? Both of them are correct. The difference is which one to be considered as a read, which one to be considered as a reference. Because it really depends on how you look at the problem. If you are here, it looks like you have insertion. If you are here, it looks like you have a deleted character because you cannot have a match with that character. Okay? So that is one of the most important points to be considered when you develop your software. Okay? So you might see a really different result between two software, but both of them are correct. All right. So talking a lot about edit distance now, we can clearly see that the Hamming distance is a special case, right? Which is one part of the problem, which is comparing this with that. That is Hamming distance. Although we do compare this with that, but we don't consider the Hamming distance over here. For example, I don't say this is a Hamming distance of 1, this compared to the first one. What I'm doing is quantifying which one is providing the largest number of matches, regardless the Hamming distance. So the matches over here is not giving me 0 Hamming distance. It's giving me 1, 2, 3, 4. So this is a Hamming distance of 4. But I'm still considering that because providing me the largest number of matches, which is this. And this combined with that, that would be the result. That would be the things that we are looking for. So Hamming distance is a special case of the edit distance. All right. So now, do I really need to do this every time I need to calculate edit distance? This is a very expensive approach. And if you know computer architecture, if you study computer organization, you know shifting is always expensive, okay? Doing a shift to this version multiple times is going to cost you a lot. And then doing the XOR with this and every single copy of that, that is a lot of work. And think about this as 1,000, million long. 4 million long as nanopore, right? That will be too much to be handled. And that's why when we calculate the edit distance, we don't do it that brute force approach. Why we call it brute force? Brute force meaning I'm trying everything, all possible ways, all possible solution. And this is exactly what I'm doing here. I'm trying all possible ways. I'm trying to shift by 1 step, 2 step, 3 step, 4 step, 5 step until I finish the length, complete the entire length, right? And then I'm doing in the opposite direction. And that's brute force, really, because I'm trying everything, every single solution. So instead of doing that, the space of enumerating all possible shifted copies is huge, especially when the sequence is very long and we cannot afford the brute force solution, right? Now, instead, we have to use dynamic programming. Dynamic programming. And this is a very famous term in computer science. It's an optimization technique used in computer science and mathematics to solve problems by breaking them down into smaller, overlapping subproblems. Okay? Smaller, overlapping subproblems, right? There is another approach. I mentioned it maybe in the first or second class, called divide and conquer, right? So divide and conquer, what's this trying to do? Trying to break down a very large problem into much smaller problems. But they are not overlapping. They are not overlapping. So we divide a bigger problem. Do you need this area here? Did I erase? You may notice in the online recording, I have almost all the videos are blurry. You cannot see whatever I draw here, unfortunately. So there was one setting in the Zoom that we could fix in order to fix this issue. I thought it's from the camera itself. But then there is something called portrait lighting. I need to remove that option. Hopefully you'll see it clear in the recording. Yeah, if there is a big problem, like sorting, for example, you would like to sort a very large array. Okay, you have several elements like integer numbers, for example, 90, 10, 40, 3, 5, and you'd like to sort this array. One way to do that, there are a lot of algorithms to do it, right? One way to do it, bubble sort, for example, or merge sort. Could be, what are other ways to do sorting? Quick sort, excellent. There are too many things, right? One way to sort this is to break it down into multiple arrays of 2 elements. Every 2 elements, just get them in different array. 20, 10, 40, 3, 5, maybe if there's something here. Okay. Now sort each of those sub-arrays separately. So 10 and 90, 3, 40, 5, and 7. Now, individually, they are sorted, but globally, they are not sorted. And then merge this and this, and then try to sort. Merge this and this, try to sort. And that is one way of looking at the divide and conquer. Okay? Here, they are not overlapping. Really, each 2 elements are in totally different array. But when we talk about here as dynamic programming, it's really overlapping problem. Okay? And when we look at it, it's totally different way of solving this problem. Now it becomes algorithm, of course. Okay? Too much algorithm. So it's very important to understand that this is smaller overlapping subproblems. And you can see the overlap over here. The overlap is really clear. Think about any character anywhere. The exact same character has been compared to the exact same character over here multiple times. Okay? Why we do that? Because the exact same character in here or in here has been compared to all the neighborhood characters, either in the right direction or left direction or the corresponding direction. Okay? And that's why we have a lot of overlaps between those subproblems. We will see that clearly in the next slide. We have very nice example. We go step by step and see the overlaps. Okay. Now, another way to look at the dynamic programming approach as a tabular computation. What does mean tabular? Table. Excellent. So it's a way of computing using a table, the edit distance between sequence 1, sequence 2, where we solve problem by combining solutions to subproblems. So we have solution to each subproblem separate, and then we combine them together. But remember, in dynamic programming, they are already overlapped. Okay? All right. Enough with the theory. Let's go with getting our hand dirty. So we have an equation over here, or the algorithm of calculating the edit distance. And this is very important. We have a table. In the table, the first row, we place the text that we would like to compare with. In the first column, we place the other text that we are comparing with. Okay? So what is the size of this table? You can clearly see the number of columns are equal to the length of the text plus 2, right? And the number of rows are equal to the text length plus 2. Okay? But normally, when you do the table, you don't include this column and you don't include this row. Okay? We draw them outside the table normally. So the table boundaries start from here all the way to here. Okay? And those texts normally are placed in memory location somewhere. Like it could be array, it could be any data structure you place in your program, right? You just read them and then you build this table. Okay? So when I ask you what is the size of the dynamic programming table for two texts of length 20, normally it's 21 times 21, right? So the text length plus 1, not plus 2, because we said this would be the calculated table. And here, normally we don't calculate anything. We just read from the memory storage or any data structure. Okay? All right. Now, how we calculate the edit distance for this text and this text? The algorithm is very simple. It says we need to initialize the first row and the first column, assuming this is the table only, okay? Excluding the text columns and row, okay? Now, how we initialize this row? Look at the equation over here. It says E is now the table over here for the index I and 0. This is normally row and this is column. So this is going to give me the first column over here. I iterate over the rows, but still in column 0. And this is exactly what I have in here. All of this should be equal to I. What is I? Is the index I have over here, which is the index of the rows. Okay? So what I'm doing in theory, just copy this column over here. How about the row over here, which is this equation? It says the row number 0 and the column J, so this is row number 0, this column J, 0, 1, 2, 3, and so on, equals J. It means all of this would be equal to J, and J value is here, 0, 1, 2, 3, 4, 5. Remember, anything in computer science should start with 0, not 1. Don't make mistake and count this from 1. Both of them should start from 0, because 0 is a thing in computer science, is a place in the memory. It's a storage location, okay? And this is what we'll be doing for initialization step. Just copy this column over here and the row over there, okay? Now, what is next? We already finished those two equations from the algorithm, and this is what we call edit distance algorithm. Now, the next step to compare every character from one sequence with another character from the other sequence. For example, this and this, this and this, and so on. Now, how do I compare them? It says consider the index I and the index J from the other sequence. Meaning, I would like to compare this C, okay? I need to compare it with C, T, C, A, and so on, with every single character in here. Now, let's take the first character, C and C. How I do the comparison? So it says, if they are the same, then do this. If they are not the same, then do this. Okay? Is C similar to C? Yes, then we are going to apply this equation. And what does this equation telling us? You have this figure over here. The figure mentioned the index I minus 1, J minus 1, which is this one. Okay? It means if the two characters are same, then I'm going to get the copy from here, the value, whatever the value here, to here. Okay? In the table, if C is similar to C, then I'm going to get the value over here to here. Okay? And we call it upper left diagonal. Okay? Upper left diagonal value, which is this. So this is upper, this is left, and this is upper left. Okay? That is in a case that two characters are similar. Okay? Now let's see the T and C. The T and C. The T and C. Are they similar? No. Right? C is not similar to T. Then which one we're going to apply? The else condition. Right? And what does it say? It say 1 plus the minimum out of these three values. And if you wonder what are these three values, you can see the color. This is a pink, which means this. This is a blue, this, and the brown in here. Or maybe orange. I don't know. And this slide, it's dark orange. Right? So what does it say? It say the value in any cell, if the two characters are not similar, then it's equal to 1 plus the minimum out of the three neighborhood cell. Let's see it in the example. Now, the C is not equal to T. What should we do? We should go to the else condition. Then this value, this one, the empty cell, equals, underneath all of this. Okay. It's equal to 1 plus the minimum out of the three neighborhood cells. Where are they? This, this, this. So we have 0, 1, and 1. What is the minimum out of the three values? 0. Then 1 plus 0 equal 1. Then this should be 1. Let's see. Yeah. Oh, sorry. We're calculating different things. So we are not here. We already finished C and C, right? We are C and T here. So we said this is C because this is coming from here, right? Because they are equal. When they are equal, we just copy the value here. But now we are here. We are comparing C and T. So we should consider these three values, not these three. So it's 0, 1, and 2. Still, what is the minimum? 1 plus 0 equal 1. So that is the value of 1. Okay? So C and T. Now let's take C and C. It's easy because we just copy the value. So C and C are equal. So we'll just take this value as is all the way down here. Okay? Now let's take another value. For example, C and A, this one. I wish we could, maybe we could. Yeah. It will be easier for us. Come on, go up, go up. All right. So assume we are comparing this and this. So C and A, they are not similar. So I'm going to consider this value, this, and this, right? So 1 plus the minimum of 3, 4, 5, right? What is the minimum of this? 3, and 1 plus 3 equal 4. Let's see if it is 4. Yes. Okay. And we continue doing that for the entire row. Now, there is one important thing while we calculate. I think there is an algorithm for doing that. You have to do it 3 times. The third time will be stopped here. If you do it next time, it's stopped right place. All right. So now, assuming we calculate the entire row, there's one important step we have to do. What is it? You have to remember how you come up with that cell. You have to remember how you calculate that cell. This cell was based on this, so we have an arrow this shape. This is a very important step. And you have to do it for the entire thing. Okay? Now, what does it mean? What does this or this arrow mean? Excellent. We are focusing. Each of this movement really has a meaning, and you can see from here. If I consider the value over here, first, let's agree. If we consider the value over here, it has 2 meanings. If I consider the value over here, it has 2 meanings. If I consider the value here, 1 meaning, deletion. If I consider the value over here, 1 meaning, insertion. Okay? But what are the 2 meanings of this value? Now, this value, I could use it when the 2 characters are similar, right? Which is exact match. For example, this C and C are same, so I copy this, right? However, I could also copy this value when it is a minimum. When it is a minimum, I could copy it and use it plus 1 and use it in here. So that's why when I use the value in here and the characters are not same, it means substitution error happening. So as you go gradually, you build this table, you can trace all kind of operation. You can trace everything is happening. Is it insertion, deletion, substitution, exact match, and so on, with using those arrows. So basically, you are not doing all the shifted copies, and you are calculating this table, and you are doing all of this in a very simple way of doing it. Much simpler than the brute force solution. And we will see why. As soon as you build the next column, continue doing the exact same thing, there is no difference. You start building, you continue with building the exact same thing. For example, let's take another example. I wish I didn't bring it down. For example, T, I'd like to compare it with A in here. T and A are not similar. Then I'm taking the minimum of the 0, 1, and 1 and adding 1 to that. The minimum of this value is 0, and then plus 1, 0 plus 1 is 1, and then that's the value, right? Then I'm going to draw arrow from here to there because I use this value in addition to 1. Yeah, that's the arrow. I continue doing the exact same thing. I complete the entire table. Now, where are the overlapping problems? Where are the overlapping problems? So now when I compare the C to all those characters, it is really part of the solution of comparing the C and T together to the entire thing, right? Because C is this row, and when I ask you to compare C and T with this text, you are going to build these 2 rows as well, right? And then this becomes part of the solution. Likewise, when I give you these 3 characters. Now, if I give you C, T, C, Now the C is part of the solution. The CT is part of the solution. The CTC is the solution, right? So every single step I'm doing here is part of the bigger problem, which this is the bigger problem, right? And I'm dividing it into overlapping subproblems. This is the first one. This is the second, the third, fourth, and keep extending. And you can see as we grow, everything we build in any row will be used later on, right? So this, the exact same table you will get if I tell you the second sequence is C, T, C, T, A, only, up to here. If I give you this text only, right, and ask you to compare it with that, you're going to build the exact same thing over here. There is no difference at all. And that's why this becomes part of the solution for the bigger problem over here. If you solve this, and next question, I ask you to compare this with that, it doesn't make sense to build the table from scratch. You just use everything you build in here and you just extend it, right? This is very important why we are using dynamic programming table, because any solution to subproblem, it's part of the solution for the bigger problem. All right, so we've been explaining a lot about this edit distance, but at the end, where's the edit distance? Where's the edit value? How many edits do I have? Which number out of this entire table? Right? This is the goal, why we are using this algorithm to give us the edit distance. Any guess? Very close. Need to tweak a little bit. So as we move from the very first character all the way to comparing to the last character, and we track all the operation that we are doing. And remember, your friend was very close. He said the minimum number of movement, right? That is the definition of edit distance. Now, the minimum number would be exactly this cell. Always. The minimum number would be anything in that cell. So what is the number here? 2. Means the edit distance is 2. It means the optimal number of edit operation or the optimal number of edit value for this to be exactly same as that is 2. Let's see, maybe by eye you could capture that. So C is same, T, C. Now here we start seeing difference. So probably we are replacing the, how many A's we have? 4? 4? Okay, we are not replacing. It looks like we are adding T over here. So we are inserting the T over here. That's why now the A's come similar to A's. And then we have the G and C, and this G is extra because we added one character over here. So now the length of this is similar to this. So really there are 2 changes, which is the T added, and there is the G added over there, right? And it's really matching the number we got out of there, okay? Where's the calculated distance? We said this one, okay? Now, what does everything we did here mean? So this, the edit distance value, okay? This, we call it dynamic programming table. And we agree on the size of the table to be the length, we already erased it, the length plus 1 times length. This is for the sequence 1, this is for sequence 2 times 1. That is the size of the dynamic programming table, okay? Now, those are the input sequence pair. This is 1 and this is 2. Now, there is no restriction on the length of the 2 sequences. Could be one of them 10 characters, the other 100, million, 1,000. There's no restriction at all, okay? Now, what does this arrow mean? We will discuss that. Either insertion, deletion, substitution, or exact match. All right, so next time, Maybe we can stop somewhere here for the lecture. We'll continue with now the assignment and the homework. Next time we're going to use those arrows. Until now, we provide the value of the edit distance, but we didn't know where are the edit. Okay? We know they are 2, but where are they? We count ourselves manually by hand, and we figure out that there is a T added here and there is G added over there. But can the table tell us where are they and what type are they? The short answer, yes, and we will see that next lecture. We will see how the table can really tell you quickly where are those changes and what type. Are they insertion? Are they deletion? The table can tell you that. Okay? Yeah, this is very bad. So Georgia State University has a very nice rule. You have to change the password every 120 days. Okay? And every time you change it, you need to change everything with it. And this is part of it. All right. So, in short, edit distance should provide you 3 information. The first one, the edit distance, right? Which we are looking for. Second thing, the type of edits. Now, this is the number of edits. This is the type of edits. What else do we need? Excellent. The location of those edits. And this is what we should learn in those 2 lectures. Okay? So this is really what is used in Google search. Google search does not use Hamming distance. It uses edit distance to figure out this kind of thing. Oh, I'm going very long way. Do you remember the Google search? Yeah. So edit distance is really the thing that is used in here. So every time you type, calculate the edit distance with this word along with the entire dictionary and try to figure out what is the closest word for that. Okay? The one with the minimum edit distance will be suggested to you. Okay? All right. Now, we have a couple of minutes, so maybe we can discuss the assignments. And maybe it's good to exit the PowerPoint and just go to the right slide. And do this. Then we have to be sure that this is shared. Go back to Zoom. And then we share right screen. Okay. And let's hide this. So as we discussed a week ago, the deadline for the review paper is due today. So you probably see the submission link in the table of content. So please submit it. You have until the end of the today. The submission, very simple in iCollege. Just produce a PDF document out of your paper, regardless if it is Overleaf, if it is Google Doc, whatever you were using for text editing. Please submit a PDF. You are free to, if you already read the paper and you did some annotation, some handwritten text or with marker or highlight in the PDF itself, you are free to save that and submit it along with the draft of the paper. Okay, that will going to highlight part of the efforts that you spend when you read the paper. Okay. If you need an extension for the deadline, do you want? How many days? Wednesday. Is that final? Okay, yeah, let's go for that then. Then the deadline extended by the end of Wednesday. Okay, Friday. No, Wednesday. Okay, we can go for Friday, but you have another programming assignment. Now, this is extremely easy. If you complete really the programming assignment, number one, this won't take you, I would say, like 30 minutes or so. Okay, you just need to apply for loop to the sequence you got from the FASTA file and extract the sequences in any way you like. Let's see the detail. It's really easy one. Assuming you did programming assignment perfectly. If you didn't do it, you still have that trouble. Okay. Now, extend your previous Python program, which is assignment number one, to do the following. Very two simple tasks. The first one, choose one indexing algorithm out of this. And they already make it easy for you, so you know which lecture to watch. It's up to you. You could go with the easiest, which is this, because this is already involved in any of those. If you want to do any of these, you have to do this. So it's up to you to go with the first one. It's up to you how curious you could go far, okay? So just pick one of those, right? And you apply it to the FASTA file, assuming you're already being able to read the FASTA file to recognize where's the sequence, where's the identifier, right? And then you have to build a hash table and save the seeds that you extract using this indexing method along with their start location. So just build the hash table out of the seeds that you extracted, and then use the exact same indexing algorithm to process the FastQ file. Remember, in here we save in hash table. Here we don't save anything. We use every single seed we extract from here to query the hash table. But now it's not required to do the query thing, okay? Just apply the algorithm. And during the lecture, I already give you the algorithm. And we explain it with example, with too many things, right? Should be straightforward. I can imagine just for loop, you iterate over the sequence, you extract k characters, you store the location. But remember, when you consider the location, you have to consider starting from 0, okay? So the first character in any sequence is 0. There are some students consider the start location as the number of seed, and this is wrong, okay? Let's maybe take an example to make it easier for you. So imagine you have A, C, G, T, T, A, C. That's a nice song, okay? And I would like to extract K of length 3. So 1, 2, 3, and so on. So what is the start location of this guy? 0. What is the start location of this guy? 1, 2. How we know that? Just look at the first character in the C. In here. What is the index of this character? What is the index of that character? What is the index of that character? So this is 0, 1, 2, 3, 4, 5, 6, so on. Very easy, right? Yeah, don't mix up the index of the character with the order of the seed. So this is the first, second, third, but once you use minimizer, for example, you're going to use some of them, not all of those. And then this index will be clear that if you pick it correctly or not, okay? So for example, if I choose this one as minimizer seed, the index of the character here is 2, but the order of the seed is 1, right? This is what I meant by some students are doing that wrong way of thinking about it. So if I pick this seed as the one to be stored, for example, I'm using minimizer, so all of those are overlapping seeds. But the minimizer, I pick some of them. For example, assume I picked this one. The index of the first character here is is 2, because this is the character, 2, right? But the order of that seed is the first one in the list. So it's 1 or 0, maybe, depends on how you look at it. Which number to be stored? 2, not the 0, not the 1, not the order of that seed in the list, okay? It's the index of the first character in that seed. So this first character, what is the index of it in the original sequence is 2, then it should be 2, okay? Don't mix the thing up. Hopefully this is clear. And this is due in 7 days, okay? I'm very flexible in the dates, can extend as long as you're enjoying the course, you're enjoying the way you're applying it. Please don't copy from anywhere. Don't copy from ChatGPT. Don't even use it, because most of the paper we discussed are recent and you will not get a correct answer from ChatGPT, okay? You can try it yourself. I try it myself. Give me all the minimizer seeds out of this sequence. It'll give you something wrong, okay? So be careful. And it really doesn't need to use ChatGPT. The source code is very simple. You can think about it. Just rewatch the lecture. Hopefully you'll figure out an implementation yourself. Okay? 7 days enough? Yes. Up to you. Doesn't matter. Doesn't matter as long as all the parameters are variable. Don't fix based on the data. Okay? Don't fix the K and W. If you are using minimizer, don't use K and W of certain value. Don't assume K is 10 and W is 3. Okay? Just make it a parameter. K and W, whatever the user provide, should work. Okay? But please make it clear which algorithm you pick and what are the parameters and how to run it. That's a very good practice, even as software engineers. So always have a readable, very friendly README. Okay? And README, if you are using GitHub, you can use a lot of annotation to make it colorful, organized, sorted, and so on, right? You can make even header, headlines, and so on. So try to practice that in GitHub. It will be very helpful, okay? Any question for the assignment? We will see if we need really to extend this or not. But to me, really it will be 30 minutes workload. It's not that heavy. Again, you're not going to query the hash table. You're not going to identify the location of the sequences. You're not going to do edit distance yet. We are going to do that, but in the following weeks, okay? Going back to this, you still want to extend it. Okay, so we can go up to Friday, right? We have up to Friday. Please don't extend it more because we'll have progress 2, progress 3, and so on. Again, there's no grade. I'm fine with submitting very small progress, assuming you are busy now. But as we move with the semester, you'll get busier and busier, right? Have a midterm, final, and so on. Okay? Again, the goal of all those assignments just for you to enjoy the experience, to practice it in your hand. So please give yourself some time. Try to enjoy what you are doing. Try to understand why we are doing it. You might come up with a new algorithm or something to improve the existing algorithm, and then you could publish paper out of it. All right? Thank you so much for now, and I will see you in next Wednesday.